Okay, so I will introduce you. So, our first speaker today of the last session of our international workshop of quantum possible machine. The first speaker today is Yuxuan Du. Uh, Yuxuan is currently a assistant professor at the CS and Physics Mathematics Department at Nanyang Technology University. And Yuxuan is one of the leading young researchers in this area of quantum machine learning, has done a lot of nice works in quantum machine learning and also AI for quantum science, a new direction. And today we are very happy to have Yuxuan here. Okay, so Yuxuan, you can start. Yeah.
Okay, thanks for the kind introduction from Xin. And hi everyone, this is Yuxuan from CCDS and SPMS of Nanyang Technical University. And today I'm very happy to introduce some of our recent research comes. And I like to call this presentation as efficient classical learning surrogates for quantum circuits at scale. And at the very beginning of the presentation, I like to first provide a one-page summary, which help you better understand what this presentation is talking about. Actually, the main topic of this presentation centered around our recent work published on Nature Communications. And this work is completed by collaborating with Minxiu and Dutch. And actually, you can think of in this paper, we propose a very new concept called classical learning surrogates. And as we know, there are multiple ways to decompose existing quantum AI models. And if we adopt a way of about how do they training and how do they implement, and we can obtain four categories. The first one is that both the training and deploying conduct on the quantum side. And a typical example in this category is quantum neural networks. And for the rest, the second category is training classically and deploy quantumly. And the third one is training quantumly and deploy classically. And classical learning surrogate falls into this category. And as we will see later, and classical learning surrogate can indeed provide quantum advantages in certain problems. And for classical learning surrogate, so far we have several results. Besides this work, at the very end of this presentation, I will also introduce the three others about classical learning surrogates. Okay, now let us start our presentation. I think the key motivation behind classical learning surrogate is asking a key question: how to understand quantum computers at scale. Why we ask this question? As we can see, the progress of quantum hardware is rapidly evolving, right? You can see so far we can access many powerful quantum computers with more than 100 qubits. But this advance invokes a new issue, right? Like how to understand the behavior of these large scale quantum systems as conventional approaches become expensive or incapable. Why I say that? Recall that traditionally we can devise our quantum algorithms all the way about how to understand quantum computers in two approaches. The first one is using classical simulators, right? You can deploy your quantum algorithm purely on the classical side. If everything works well, you can deploy your algorithm on quantum computer and to test its performance. But now, if you are working on a quantum system or you are working on a quantum task involving more than 50 qubits, actually, these classical simulators become invisible, right? Because you can no longer use like state vector simulators to brute force simulating the corresponding results. Although you can use like tensor network or near Clifford simulators to do these tasks, but these two simulators can only provide efficient solutions for specific states, not all of them. So there is a trade-off between the time complexity and memory complexity as well as the corresponding precision. An alternative solution is use like tomography-based approaches. More specifically, you can route a quantum computer on cloud service, and you can conduct your research on the everything on the quantum side. But as we know, the available quantum computers are very rare worldwide. In other words, most of us cannot afford the cost to rent a real quantum computer. So taken together, we encounter a very critical issue. So how to understand the behavior of large qubit quantum circuits in an efficient manner without invoking so many quantum resources? And this paper or this presentation focus on to answer this question. And here we narrow our scope. We only ask, is there any efficient classical machine learning models that can well predict the linear properties, or in other words, the mean values or observable estimations of large qubit quantum circuits? And here we provide positive affirmation. And yes, indeed, we can use classical learning surrogate, or you can also call agent, emulator, or learner to achieve this goal. Okay, and now let us formalize the corresponding problem. Here, actually, we focus on a class of quantum circuits, which is composed of birotational Z gates and Clifford gates. These two set of gates can actually is universal, right? You can decompose any given quantum circuits into rotational Z gates and Clifford gates. And the learning procedure or learning objective is shown in this picture. At the beginning, the learner, I mean the classical learner, doesn't know the layout of the quantum circuits. The learner only knows the like okay, there are D rotational gates and many Clifford gates, and the learner can fit different rotation angles or different classical inputs to the quantum circuits, and then conduct some single copy and incoherent measurements to collect the corresponding information. So this is a way to interact with the quantum system. After that, the learner can build a data set, right? Because the learner can fit different inputs and collect corresponding measurement outcomes. In this way, by repeating, the learner can build a training data set. And once the data set is prepared, the learner will try to mimic the behavior of these quantum circuits. And in the after training, during the prediction stage, given any new inputs or given any new rotation angles of RJ gates, the learner should be capable to predict the corresponding expectation values purely on the classical side. So at the training or at the inference stage, the learner cannot allow to interact with the quantum system anymore. So here we focus on encrypted circuits, and we define the number of RJ gates as D, and we define the number of Clifford gates as G minus D, right? So in total, there are G gates. And how to define the efficiency? So here we define the efficiency at here. So for the classical learner, especially for efficient classical learner, the required computational complexity of training and the inference stage should be at most polynomially scales with the number of qubits and the number of rotational RZ gates denoted by D. So this is the definition about the computational efficiency. Okay, now I'd like to address if we can design some efficient classical learning surrogates, then we'll obtain many crucial implications. The first one is about enriching quantum learning theory. Because okay, you can see currently we have many good results about the capability of quantum learning models. And if we have some results about the capability of classical learning surrogates, and we can enrich the corresponding fields. And the second one is if we can deliver some efficient classical learning surrogates, and then we can benefit many practical applications, especially those around the expectation value calculation or something about mean value estimation, like quantum certification, quantum shadow estimation, quantum simulation, or variational quantum algorithms. All of them actually can be recast to do something about compute the expectation values, right? So if we have classical learning surrogates, we can substantially reduce the required quantum resources, because we can move the computational burdens on the classical side. Okay, now let me introduce our main theoretical results. Okay, based on our problem setup, actually the classical learning surrogate or the classical learner actually learns this concept class. Because we are focusing on parameterized quantum circuits, right? So can be denoted by rho of x, and here the parameterized state rho of x is formalized by applying a parameterized quantum circuits U of x, which is composed of d RZ gates and many Clifford gates to a fixed input state rho 0. And of course, a classical learner doesn't know the circuit layout, so the circuit the architecture of this unitary can be varied. So this induces concept class, and indeed we have a target concept, and the purpose is to build a classical learning surrogate to try to find this target concept from this concept class to achieve a small prediction error, which is denoted by epsilon. So on average, we want to show this research aim, which is to derive the computational complexity of the classical learning surrogate to achieve this absolute prediction error. Okay, and to achieve this goal, we decompose our central aim into three sub-aims. The first sub-aim is to understand the learnability of this concept class F in terms of the sample complexity. In other words, how many training examples do we need to obtain this hypothesis function H to achieve an absolute prediction error? And the second sub-aim is to derive the corresponding computational complexity. In other words, how many time do we need to induce this hypothesis function H? And the last one is about the contraction, like how to design an efficient classical learning surrogate to match the above bounds. Okay, now for the first sub-aim, here I only show the proof idea. I will not go in detail, and if you are interested in, you can read our paper. And for the first sub-aim, which is about the derivation of sample complexity, our key result is that the D over epsilon training examples are sufficient and necessary to learn F. In other words, to mimic the behavior of these quantum circuits. This is good news, right? Because we can see the required sample complexity only polynomially scaling with the number of rotational RZ gates and is insensitive to the number of qubits. In other words, in terms of the sample complexity, actually we can indeed find some classical learning surrogates to be very efficient to learn large-scale quantum algorithms. And the key technique to achieve result is using carving and packing net, hypothesis testing, and final inequality. By combining these technical tools, you can separately show, okay, for lower bound, the polynomial training examples with respect to the number of rotational RZ gates D is necessary. And by using the result of carving number, you can show, okay, O of D is sufficient to obtain a good hypothesis function to achieve this absolute prediction error. Okay, and for the computational complexity, we recast this problem to some problem in complex theory by building connection with BQP circuits. And in this way, actually we will obtain a negative result. So even though the classical learning surrogates are sample efficient, but it's computational hard. Because indeed we can find some quantum circuits that no efficient classical learning surrogate exist. In other words, no polynomial time, no efficient, the classical learning surrogate should use at least maybe a exponential runtime to obtain a good prediction error. Okay, now from the perspective of computational complexity, the result is very negative. So we should redefine our target. We are asking if we can impose some practical conditions to make the classical learning circuit efficient. Because in the most general case, it's not efficient, right? So we need to narrow our objective. And in this way, indeed, we can deliver efficient classical surrogates for many practical problems. And this corresponds to our sub aim 3, right, as shown here. Indeed, if we impose some mild assumptions, we can deliver a very efficient classical learning surrogates. And this picture demonstrates the implementation of the proposed classical learning surrogates. You can see it composed of two parts. The first one is data collection. And at this stage, we just input different rotation angles to the parameterized quantum circuits and conduct a poly-based classical shadow. And then we can build a training dataset with n training examples. And then once this dataset is prepared, we can use this dataset to build a kernel machine. And this construction is conducted purely on the classical side, right? Because for this part correspond to how to build the corresponding feature map depending on the input angles used in the training dataset. And then we can make a combination of these classical representations with the shadow estimation to build a very efficient kernel machines. And the definition is shown here. This is a formal definition of the proposed kernel-based classical learning surrogate. And you can see the formula is composed of two parts. The first one is a truncated trigonometric monomial kernel. And the second one, the function of g actually corresponds to a shadow estimation. So this is very straightforward, right? Because for any quantum state, uh, you can use the corresponding classical representation to get to get a estimation. So key button is here. So why should we build this truncated trigonometric monomial kernel? Actually, the key insight is from the polytransfer matrix. Actually, if we rewrite the explored parameterized quantum circuits by polytransfer matrix, actually you can build a very good formalization to say, okay, indeed, if you use kernel, you can easily compare the similarity between different quantum space in the high dimension feature space. And the condition we imposed is the smoothness. As we discussed before, for general circuits, there is no efficient classical learning surrogates, so we must introduce some mild conditions. And the condition is about smoothness. We require the gradient norm of the explored quantum circuits should be bounded by a constant C. So this is the only requirement. And in this way, and we can show the efficiency of the proper method. And the proof, the key proof is shown here, right? To derive the prediction error, we need to decompose our derivation into two parts. The first one is bounding the truncation error, and the second one is bounding the estimated error. And for the truncation error, we need to use this condition, like the introduced smoothness condition, and then we can show a good bound. And for the estimation error, this part is still induced by the poly-based classical shadow. So we can use the result from the shadow paper to obtain the corresponding bound. And then by combine everything together, you can obtain, okay, the proposed method is simple and runtime efficient, especially when the constancy is very small. Okay, I like to address that. If we extend our setting from rotational Z gates plus Clifford gates and to a new setting, like we can induce many T gates, all the derived results will keep unchanged. This is very important because for classical simulators, as T gates are very important resource operations. So if the required simulation runtime actually exponentially scales with the number of T gates, but for classical learning surrogates, it's insensitive to the number of T gates. So this is a key difference, and this difference gives the quantum advantages of classical learning surrogates compared to all fully classical methods. Okay, and we verify the effectiveness of the proposed kernel-based classical learning surrogates, and we verify its effectiveness on two tasks. The one is to predict the behavior of n-qubit rotational GHZ states, and we conduct a simulation on like 60 qubits. And the next one is to show how to use classical learning surrogates to advance the optimization of VQE, because we can move most of parts of the optimization purely on the classical side, and we can see classical learning surrogates achieve a similar performance of the conventional VQE methods. Okay, now I'd like to address the rest three papers as we discussed at the very beginning of the presentation. So previously, our key focus is how to use classical surrogates to mimic the behavior of ideal quantum processors. And recently, we extended the capability of classical learning surrogates. We use them to predict the behaviors of noisy quantum circuits. And in this context, we proposed two classical learning surrogates. The one is still a kernel-based method, and another one is regression-based method. And this classical learning surrogate focus on the setting with correlated input, and the data distribution can be arbitrary. And the only requirement is that the input the ranges of the inputs should be restricted and we verify the effectiveness of the proposed two surrogates on real hardware. And the first one is to advance again the pre-training of variational quantum eigensolvers, and another one is to advance the study of the phase identification of non-equilibrium quantum systems. Okay, and now at the very end, let me summarize this presentation. And there are many open questions behind classical learning surrogates. The first one is there any probably evasion learning surrogate beyond the packet learning setting as we focused in our recent works? And the second question is, are there more applications of classical learning surrogates beyond what we have explored? And the third question is there any advanced classical learning surrogate beyond the mean value estimation, like do something like sampling tasks? Okay, that's all the content I like to share. Thanks for your listening.
Yeah, thanks for the nice talk. We have time for several questions. So, any questions for Yuxuan? Yeah, I have a quick question. Um,
Mm.
so from your research, like what kind of things is kind of more difficult to predict or may cause some like larger predict error?
Okay,
What kind of
the most
system or circuits? Yeah.
yes, number of rotational gates. Actually, you can think from learning perspective, if you have
Mm-hmm.
many rotational gates, actually you cannot make a good truncation. So unlike resource theory like T gates or resource operations, actually for learning perspective, the parameterized gates actually are resource operations. So if your circuits contain many rotational gates, and
Mm-hmm.
then indeed the learning hardness will be increased.
I see. I see. Okay.
Yeah,
And second question is like, um, for the predict objects, right? There can be lots of things like the observable trace oral, and also
yeah,
for example, the state property like the entropy,
yeah.
or even the locality of the Hamiltonian. So, like, what kind of is there any difference? Like, what kind of objective you think is kind of more suitable for this setting, more easier to predict? Any opinions?
Okay, yeah, this is a very good question. As we discussed here, actually, if you want to
Hmm.
explore some nonlinear properties like
I see.
the trace of case power of a state, actually, you can always build a quantum circuit to measure it actually in a linear manner. So actually, you can use multi-copy methods, and you can actually, if you want to explore a nonlinear property of an unqubit state and you can actually build maybe two times n quantum circuits to derive the corresponding properties. And actually, this corresponds to introduce correlated parameters like correlated inputs, cause like you actually you want to calculate trace of rho of x squared, and then you can introduce multi-copy and to make some duplicate and to measure a single observable and then this create boundary setting. But for this setting, actually, I think it's much more difficult than just compute the simple linear property of a quantum state, because in this setting, you must impose another constriction. the restriction is that you need to restrict the range of the inputs, like the rotation angle can never be from minus pi to pi. You need to restrict it to a very small region. And in this way, you can deliver efficient learning in surrogates.
Okay, thanks.
Yeah.
Yes, makes sense. Hmm. So any more questions from the audience? Okay, so no, if like audience have more questions, you can ask during the discuss session. Okay, so Mark, I will hand it to you. Yeah,
Good.
thanks, Yuxuan,
Thank
for the
you.
next talk. Yeah,
Oh,
yeah,
okay,
yeah.
Yeah,
great.
thank you for your talk. So our next speaker is Ge. Um, so you are you a professor at Hong Kong University now? Sorry for not knowing that.
Yeah. Hi, Mark. Yes, I'm now assistant professor at Hong Kong University, Guangzhou.
That's great. Okay, congratulations. So
Yeah,
yeah,
thanks.
I've seen some of your papers with Valerio and
Uh,
Francesco, and I'm very happy to hear about what you're going to tell us about today. So please go ahead.
Sure. Yeah. Yeah, today I'm going to talk about like retrodiction, and I'm going to figure out like the difference between proper mixtures and improper mixtures. I'll
Sure.
explain that later. So let's begin with like what is knowledge? So in the classical Bayes theory, we often represent knowledge, such as facts or correlation or simply some belief, with with probabilities, and these probabilities are kind of subjective probabilities. For example, if you believe something is so true, you set the probability to be one. If you have some correlation, then yeah, you have to like correlated probability. If you have some, say, the coin has one half probability to land on head, but say you don't know whether the coin is fair or not, but you kind of believe that it's fair. So you'll say the probability of head is one half. So this is a Euro-Bayesian interpretation of probability, or is the same as belief or knowledge. So the Bayes rule also tells us like how do we update knowledge. Consider a scenario that we want to know something that we cannot directly see. For example, I get a positive result in a medical test, and what I want to know is whether I'm sick or not just whether I'm negative or positive. So given the observed result, negative or positive, we want to know the true input, healthy or sick. And the process of the medical test could be considered as a stochastic map. And this map, say, let's say we have these figures here. The disease affects 1% of the population, and the medical test is 98% accurate. So we could do that with Bayes rule. The Bayes rule says that we could compute the probability that I am sick with like this thing is the Bayes formula. And in the Bayes formula, we have some prior belief. Yes, we have some prior belief that is 1% because the disease affects 1% population. This is our initial guess of whether I'm sick or not. And we put that into this formula, and we get an updated belief based on the fact that I get a positive result and based on the medical test is 98% accurate and the disease affects 1% population. So we compute that, and we see that it's not 100% or it's not 98%. So yeah, so in the general setting, we consider a stochastic map from some variable x to another random variable y. And what we know what we see is something on the variable y. For example, we observe the positive result, say, then we observe the probability of positive or y equal to positive to be 1. And after that, we put these things into the Bayes formula, and we call here Bayesian retrodiction, because retrodiction means that we want to know something that happened before. So we want to know the input or the cause, and we put these numbers in. And interestingly, the Bayesian retrodiction tells you a reverse stochastic map that goes from the output variable y to the input variable x, which is given by the Bayesian formula P reverse here. And from this reverse map, given any observation, we could get an updated belief of the input distribution. So this is the classical case. So I'm next going to talk about the quantum case. So how do we update quantum knowledge? So first, quantum knowledge may be quite different from classical knowledge because quantum states are on the for example, a qubit versus a bit. A bit is just 1 or 0. Then if you have some knowledge, it's just a probability of whether it's 0 or not. But for quantum states, it's on a sphere. So there are kind of more ways to represent quantum knowledge. So let's imagine some ways. One possibility is that we take a probability distribution over the whole Bloch sphere. So for every state, we know that has some probability. And the second is what we usually use is a density matrix. The density matrix, sometimes it is considered as a quantum counterpart of the probability distribution. Or there may be also some other possibilities. So let's investigate them. Say we have a probability over states. And actually, this case isn't so different from the classical case because still we could use classical Bayes rule. Say we have a prior distribution over the Bloch sphere. We take a sample which is a quantum state, and imagine we are making a measurement on the state. Then the measurement result will be given by the Born's rule, the outcome probabilities. And this Born's rule is actually our forward process. And after we observe something, say we observe the output that is y, then we insert these values into the Bayes rule, and actually, according to the Bayes reference, we could obtain an updated distribution over the Bloch sphere. And this would be our updated knowledge of these quantum states after observing the result y. So this is just what you can use is just classical Bayes rule. Let's consider another counterpart of probability, that is the density matrix. The density matrix is constructed such that it could completely characterize the outcome probabilities of a measurement. Say now the forward map is it is conditioned on the density matrix, and from the density matrix we could get a probability distribution of outcomes. However, we could observe that there is a difference between a density matrix and a probability over states, because some probability mixtures are indistinguishable with measurements, and therefore they have the same density matrix. For example, for polarized light, like 1/2 horizontal plus 1/2 vertical is indistinguishable with like 1/2, like 45, 1/2 minus 45. And some other cases. So there are ways to manage such density matrices as probabilities. And this is sometimes called the quantum Bayes rule. So the quantum Bayes rule, we don't have to read the formula here. We just need to know that the quantum Bayes rule is similar to the classical Bayes rule. It is giving some kind of reverse process. It is giving some reverse process such that when you are given your observation, which is represented as tau here, for example, if you observe the outcome y, we could just take tau to be cat y bra y to mimic the probability distribution with like one probability of y equals 1. And we could plug that into this formula, and we could get a reverse process. And this reverse process gives you updated density matrix when you observe something. So here is an example. Say our initial belief is that we have a density uniform belief, which is represented as identity over 2. And say we then make a measurement on that state as a forward process. So the first case is we measure in the 0-1 basis. So if we get 0, then our belief will be updated to 0, and if we get 1, our belief will be updated to 1. This can be computed from the formula we showed before, the quantum Bayes rule. And there's another case, like if we measure in a different basis, say plus and minus basis, then if we get plus, we update the belief to plus. We get minus, we update the belief to minus. This is actually a quite interesting feature. It's actually a quantum feature, because in classical cases, there is only one basis to measure. So there won't be like such different bases. So if we imagine you're using the previous case, say distribution over states, we can show that no distribution over states will, and it will give you the same like update behavior like this with the classical Bayes rule. So this is kind of a quantum feature. So generally, we may consider quantum retrodiction, well, not just with measurements. We could consider like a general process more than a measurement. So, and here the task is still retrodiction. We want to infer the input of some quantum process from its output. You can imagine this is like reversing a process. And usually that process is irreversible, but we could kind of get it is, well, it's kind of reverse, but it's not actually doing the inverse of that operator. This could have some usage applications, such as we could use that for noise adapted error correction. That means if you know the noise, if you have characterized the noise already, then you could use this way to kind of redo the effect of the noise. Or you can use for estimation of a quantum state where there is some noise between the state and your measurements. And also decoding, encoding processes. Well, like basically in many cases where there is something you want to reverse. So in a general scenario, this is like a more general formula for the quantum Bayes rule. And here, well, basically there exists already a formula that you could plug in your knowledge and get the reverse process. So we have presented the formula like here, but why we use such formula? The Bayes rule has like a good theoretical foundation. It could be derived from a principle called the minimum change principle, and it is also could be proved to be optimal in many cases, like the optimal way to update your knowledge. The Bayes rule and the quantum Bayes rule are mainly connected by the analogy between this formula. Well, it may not be directly seen, but if all operators commute, the quantum Bayes rule will reduce to the classical Bayes rule. And also there are many different formulations of the quantum Bayes rule, but this one called the PASMAP satisfies like a good set of axioms that is similar to the classical Bayes rule. And it has some applications I just mentioned before. And recently we also have another work that sets the foundation of the quantum Bayes rule, the PASMAP. And we show that it satisfies a similar principle we call the quantum minimum change principle. But this is not the main topic of this talk. So the main topic of this talk is to study quantum knowledge. As I mentioned, there are many ways to describe quantum knowledge. Say, suppose let's investigate like whether the density matrix is enough to describe a quantum state. So suppose we have some box that outputs a quantum state every time. And we could observe this box, the outputs, and maybe perform some tomography or something. So we could obtain its density matrix. Say we have obtained this density matrix and it is identity over 2. So if we want to make further predictions, say on the next output, the measurement result on its next output, then we could do that like quite well because the density matrix already all the outcome probabilities. However, this box may be implemented in different ways. Say, this box may have some classical coin inside it, and each time it flips a coin, and depending on the result of the coin, it will output the state 0 or the state 1. But apparently it outputs a state 1 identity over 2 because you cannot see the coin. So this gives you such a density matrix, and this case is often called the proper mixture. There's another case. See, this box always prepare a fixed entangled pure state, but only outputs one part of it and discard the other. So in this case, still, what you observe on the output side, you see identity over 2. But this is called an improper mixture. Like improper mixture means the mixedness comes from discarding another system that is entangled with this system. So these are possibly different implementations of the box, and why they are important. Well, they are not so important if you want to do prediction. However, if you want to do retrodiction, there may be a difference. Retrodiction means that after we observe the output with some measurement, we want to know what was the state just prepared. So we also consider 2 different measurements, 0, 1, or plus minus. In the density matrix scenario, as we showed before, we could use a quantum Bayes rule, and if you get 0, we update to 0, 1 to 1, plus to plus, minus to minus, according to the rules. However, if we have a distribution over states, this is different. And in this case, we could use a classical Bayes rule. We could observe that if we measure in the 0, 1 basis, it behaves the same as the density matrix case. And however, if we measure in the plus minus basis, something happens, different happens. Because if the coin gives you 0, the state output is 0. And if you measure in the plus minus basis, you get 50-50 like probability. However, if the coin gives you 1, still the 1 state also gives you 50-50 probability. So in these 2 cases, whether you have observed plus or have observed minus should not change your belief about your inner states, because these 2 states the two initial states just behave identically in your measurement. So there should not be any update. And you could also get this by plugging the numbers into the classical Bayes. The third case is more interesting because the belief now is an entangled state, and entangled state is a pure state. In any like Bayes updates, including classical and quantum Bayes rules, if you have a certainty as your prior belief, then you cannot change that at all. So there will not be any update whatsoever, regardless of what you have observed at the output. So you know that what the state prepared is exactly always a pure state, entangled state. So this tells you that the density matrix is not the full knowledge about the system. So maybe you need something more to describe that. So to resolve that this problem, we propose that we identify that the difference actually comes from some other system that may be correlated with your target system. For example, the coin in the last slide or the entangled system previously. So what we do is from the original quantum Bayes rule, where it goes from the forward quantum process to the retrodiction process, we consider another, like what we call the extended forward quantum process. And in this process, the input is extended to two systems, the system of our interest S and some reference system R, and this could be correlated. The forward quantum process now not just on the system S, but also on R, but it's acts purely on R. It's just discarding the system R because you cannot see that system. And if you use this as a forward process, we could apply also the path map. We take the same formula as a path map. However, in this case, we have a prior on both systems. And this prior we call the beta SR here. So according to this prior and this extended forward quantum process, by the path map, we could get an extended retrodiction process. And this retrodiction process could tell you if you have observed on the output side tau, then this gives you an updated belief on your input. Well, it gives you a belief on both S and R, but if you only focus on your system S, then this is a formula where you get for your updated knowledge about S. And this formula could be different from the one if you consider only the system itself. Actually, this is a purely quantum feature. In classical case, if you consider additional system that is correlated with that one, with your system interest, actually this does not make any difference with your knowledge update. But in the quantum case, there can be difference. So with this formulation, we are able to explain the difference between these cases. For example, the density matrix case, the extended prior is just the original prior. We didn't add an additional system. And we could update that with quantum Bayes rule, and it's the same as before. If we have a distributional state, say the coin case, we could represent the coin as another system, which could be 0 or 1. And the extended prior will be the following. There's a 1/2 probability that the prepared state is 0 and the coin lands on head. And with another 1/2 probability, the prepared state is 1 and the coin lands on tail. So there is a classical correlation between these two systems. And updating this with our extended retrodiction framework, we could get the same result as a classical Bayes rule. For the entanglement case, the prior is simply an entangled state. we have a quantum entanglement between the system and the reference, and this also gives you the exactly the same result that we do not make any updates. Yeah, the classical base only has a case in the middle because a classical state could only be a distribution of different states. Here are some examples. Here we are considering we are recovering depolarization noise. So the black circle, the black dashed circle is the original Bloch sphere, a section of the original Bloch sphere. And the yellow one is the Bloch sphere after depolarization noise. It will be shrinked, it will push towards the origin a little bit. And the green one is after recovery. Like here, recovery is done by using the retrodiction map we mentioned before, kind of reversing that process. So if we have the density matrix as a prior belief, the recovery will like further shrink the Bloch sphere a little bit. If you have a distribution of states, the recovery will map everything within a line segment that connects something near the North Pole and the South Pole, something near these 0, 1, 2 states. And if our prior belief is a pure entangled state, then the recovery just doesn't do anything because everything will be mapped back to the original entangled state. And if you take only consider the system of our interest, it will be a mixed state, which is in the origin. So we have mentioned that there are many different kinds of quantum beliefs. So how do we them? So we have a theorem that says if two beliefs are equivalent, if and only if such equation is true. Well, this is a general case. Maybe it's easier to consider some special cases. For example, this theorem actually indicates that if we add another uncorrelated system to our initial belief, then it's just the same as not adding that, because an uncorrelated system should not affect our retrodiction or our knowledge. Or if we change the basis of the reference system, say we have added a local unitary there, then there should not be any difference also, because what matters is only the correlations between your system and some reference system. But the basis of the reference system should not matter. This theorem also gives you the possibility to consider more complicated cases. For example, a distribution of pure states. It's a corollary that state ensembles are equivalent beliefs if and only if their second moments are equal. For example, we could use this corollary to describe a uniform distribution over the Hart sphere. And we know that it is equivalent to the uniform distribution over these 6 states, 0, 1, plus, minus, plus, I, minus, I. Because these two sets have the same second moment. Okay, to summarize, we have shown that quantum knowledge could be described in many different ways. It could be a probability distribution over states, or a density matrix, or some entanglement, possible entanglement with some other system. But generally, we have used the same framework to describe all these things with what we call the extended belief, which describes both the system itself and its correlation with some other system. Well, the difference, the insufficiency of describing quantum knowledge by density matrix has been observed previously by Popescu in 2018. And here we get that one was like a qualitative description about the difference between density matrix or knowing the basis of the states. And here we have a quantitative formulation of this knowledge. Like we gave a way to describe this difference. Also, this could be used to unify some previously incompatible ways of quantum state inference techniques, which is shown in this archive paper. And possibly this will give us like more possibilities of doing recovery beyond simply using the path map. Okay, so that's for all for my talk. Thanks for listening, and I'm recruiting PhD postdocs, etc.
All right. Thanks a lot for your talk. I'll lead off with some questions. So given that the workshop is about quantum Boltzmann machines, I don't know if you were able to attend some of the other talks. Do you have thoughts about how what you talked about today can be related to problems associated with quantum Boltzmann machines?
Well, I do have some ideas of relating this with machine learning.
Do you
It's
want
like,
to please comment on that?
yeah, it's like we have some how to say, we have got some new ideas to update information. And you know, in machine learning, like say a parameterized quantum circuit is something that like you want to update basically. So this how to say, like you have a parameterized circuit or a parameterized gate, and we could imagine that parameter could be some kind of other system that is correlated with this gate. So we could describe that with kind of the extended belief. Well, it's just quite a vague idea. It's just we could possibly use such update rules to update the values of the parameters in the circuit.
Yeah. I want to continue along these lines. So something that's come up a fair amount during the workshop is algorithms for training restricted Boltzmann machines where you have what's called visible and hidden units. And I think this can be connected to what you're talking about, where you talk about a forward process, in this context, maybe that would be, the probability of the visible units given the hiddens, and the backward process would be the probability of the hidden units given the visible.
Yeah, this is a very nice point.
Yeah. And the leading algorithm for training classical restricted Boltzmann machines consists of, iterating between the forward and back reverse processes for some number of steps. So I guess my question for you is, and maybe this is something I should know, but do you know conditions when this process is guaranteed to converge?
No.
Okay.
I know.
Isn't there
Maybe
this detailed balance I've seen? Does that come up in your work?
Detailed balance, yes. Well, I'm not very familiar with the thermodynamics
Sure.
thing, so yeah.
So I guess another question is, when we want to go to the quantum case for this kind of back and forth process, do you have a sense of how that would work?
Yeah, well, this is actually a kind of tricky question. I mean, in quantum case, the biggest problem is that we could not freely copy states.
Yeah.
So, and actually what we do have here is we're using a path map, and the implementation of the path map is, well, it's quite some problem because it's not that direct to implement. So actually, I have the idea to make these things more quantum, in the sense that we could use like quantum update rules, like quantum implementations of path map. But possibly a possible, how to say, maybe a fallback would be to describe these things with classical data, and just we change the formula of update so that we could fit better with like quantum states.
Okay. Sounds good. Does anyone else have questions for Ge?
Actually, I need to leave now because I have a meeting.
I see. Okay.
Yeah.
Um,
Okay, thank you. And well, see
Yeah.
you.
Thank you for speaking to us.
Hmm.
All right. So our last speaker for the whole workshop is Yixian. Thank you for agreeing to speak to us.
Hi.
And
Yixian.
nice to see you. So why don't you go ahead and share your slides?
Yes.
So Yixian is a postdoc, or no, PhD student? Okay, so
Yeah.
PhD student in the research group of Patrick Rebentrost at CQT in Singapore. And she'll tell us about her work with Patrick and others on quantum Escher transform. I think we don't, now we see your screen share. Great, so please go ahead.
Can you see the full screen?
So we see the presenter notes. I think you might have to mirror the, you might have to play
How about
around.
this?
Now we see it. Perfect.
Okay. Okay, so today I will give a talk on my work that's quantum version of a mathematical tool widely used in finance and probability theory, which is called the quantum Escher transform. And this work is with my co-author Calvin, also a student, and Patrick Rebentrost, my supervisor. So let's start from this scenario. When we want to assign a probability distribution to a set of events, but without any additional information, then what should we do to choose the distribution probability? Let's give this example. There are a set of 4 events, and for 3 cases of these distributions, we can see in the first case, it seems that the distribution favored the event 1 and 4, so give them the equal distribution, but not the another true. And in the second case, we can see there's only 2 and 3 events have the equal distribution. And for the final case, the 4 events has the same this probability in this distribution, so it's the uniform distribution. But how do we choose which one is the correct to describe this scenario? So we should have this concept called maximal entropy principle, which is used to measure the uncertainty of the probability distribution. And so it means that in this scenario, with these principles, if there's no additional information given to us, we should prefer the distribution with the fewest assumptions. That means we should choose the final case. It's the uniform distribution that maximizes the entropy. But if it extend this scenario to with the constraint, let's say we are given a prior state, we're given prior distribution, then it brings us to the generalized maximal entropy, which is minimal relative entropy. So this is the problem related. Given the prior distribution P and also some random variable x and constant m. We want to solve this minimal relative entropy between the Q and the P. Q is our target distribution and subject to this expectation value of the x under Q equals to some constant observable data, and also make sure the Q distribution is valid. We want to solve this problem, and here we use the method called Lagrange multiplier, and we have this stationary condition. The solution to this problem is Q star takes the form as the exponential to the lambda star dot x multiplied by the P. And here the lambda star is the optimal point of this problem, minimizing the relative entropy. So it leads us to this definition called Esscher transform classically. Then we know we are given the probability distribution P and a random variable X and also a theta, a vector parameter theta. Then we can see the Esscher transform of the P is defined as the parameterized P as the exponential to theta dot x times P. And we know the classical Esscher transform already has more application beyond this minimized relative entropy. So we have such a question. Is it worthwhile to study the quantum version of this constraint minimal relative entropy problem? So let's go to the quantum version of this problem. Here we replace the distribution P with the density operator rho, and also consider some observable H and constant M here. We use the minimal relative entropy quantum version. Also constraint to some condition here, which is the expectation value of the target quantum state sigma, and the observable H should satisfy some equation from the energy or other properties of the system, which is the M constant here, and also make sure the sigma state is a valid quantum state. Because we know in the relative quantum relative entropy, the sigma state should stay within the support subspace of the rho. Then we know that the sigma only satisfy non-zero condition within the substate of the rho. So it leads us to the main results of this problem, which is the solution takes the exponential form, which is the e to the lambda star dot h plus the log rho. This is a difference from the classical form, and there is two forms, which is one sigma within the support of rho and another within the kernel subspace of the rho, and the lambda star, the optimal value satisfies this chase form from the solution from the problem. And the proof scripts, let's go through the proof scripts. So because of the different subspace, supports, and kernel of this rho, we can decompose the sigma into two forms. One is the sigma within the support of rho is the mean form in this proof and also in the solution, while the sigma within the kernel of the rho contributes nothing to this form. And next, we want to find the stationary points. Then we use the same method as the classical problem solution. We use the matrix Lagrange multiplier. And because here the quantum state is a complex matrix, it's not so straightforward to solve it. Then how do we solve this matrix Lagrangian? Here we use the rectangular calculus method. And finally, we can solve the stationary points, which is the optimal points, satisfying the give this constraint minimal validity entropy. If we go into the detail of how to solve this Lagrange multiplier, then we can use these two important results from the rectangle calculus. And we also have another tutorial paper using this rectangle calculus to solve some other interesting problems in this quantum information. And so use this tool, we can solve, including taking the derivative and of the Lagrangian and set this equal to 0. Then we solve the sigma takes this exponential form. And after normalization, we have the final form of this sigma. So it gives this 0, 1, 1 I mentioned as the first beginning, the sigmas within the support of rho takes this exponential form. So it literally gives us this definition, the quantum version of the Esscher transform. The first figure A here give a clear picture what is the transform. So let's say we are given an input quantum state rho and also the observable H and the vector parameter theta. We can say the quantum Esscher transform of this input rho, which is the exponential to the sigma times H plus the log rho, and also with the normalization. But it's a bit different between this quantum Esscher transform and the solution to the constraint minimi validity entropy problem. Then you can see from the second figure here, there's many paths can use to transform the rho to sigma, and like the theta 1, theta 2, and also theta star here. All these are called the quantum Esscher transform. But one among these, which is the sigma star path, if you choose the parameter as the sigma stars, then you can use it to find the solution to the constraint minimal validity entropy problem. Then let's see what's the connection to the quantum Boltzmann machine. So we know the quantum Boltzmann machine is the energy-based model, always use the Gibbs states. And our quantum Esscher transform make a generalization with given a prior state rho. So you can see there is a bit difference in the exponential plus log rho, but especially if we make the rho is the maximally mixed state, then our Q Esscher will, sorry. Oh, wait. Can you still see my screen?
It's like sliding between screens. Now we see it.
Okay.
Yeah.
So in the special cases where we set the rho is maximally mixed, then the Q Esscher will reduce to the standard Gibbs form. That's what the quantum Boltzmann machine used. And also when we set the rho and H commutes, then it also recovered to the classical Esscher transform case. So potentially we are considering if we can use our Q Esscher as another natural primitive as the quantum Boltzmann machine use. And also if we want to use it, how can we make it as a hardware level? So this leads us to the second question. How can we implement our Q Esscher, this kind of new Esscher states on the quantum computers? So we use the broad encoding and QSVT technique. So we can use, if we have the broad encoding of the matrix A with the bounding of the spectral norm of 1, and also with broad encoding can efficiently apply the unitary and its inverse, then the property of this broad encoding is we apply the matrix A on the top left corner of the view, and it leads to the theorem of this broad encoding. When we are given this broad encoding, we can use this quantum singular value transform, which means we can also apply the polynomial function of this matrix into the broad encoding and use it to approximate something you want to apply. So there is an assumption we have to satisfy here because we have to use it to implement the polynomial, any polynomial function of the x. And the assumption requires us to make sure the polynomial of the matrix is bounded by the special norm of the 1/2. So using this broad encoding and quantum singular value transform QSVT, then we can efficiently implement the components in the quantum Escher transform state. So this is the second main result, which is the sample complexity of the algorithmic implementation. So let's say we using this broad encoding, then we can output this epsilon approximate broad encoding output of the subnormalized quantum Escher transform states. Then the sample complexity is kappa times the square of the log of 1/epsilon queries to the broad encoding of the input state row, and also the log of 1/epsilon queries to each broad encoding of the variable hi. Let's go through the framework of this algorithm. So the inputs are the unitary of the row, give the purification of the states, and also the unitary of each variable h, and also the parameter vector theta here. Our target is to output the approximate broad encoding of this, not a subnormalized quantum Escher transform state. Then the first step is we use the broad encoding of the row to construct of the broad encoding of the log row, which is the polynomial function of row based on this lemma 1. And secondly, we use the state preparation pair to construct a linear combination of this sigma times row plus log row. And based on the lemma 2, using the generalized linear combination of different broad encoding matrices. And finally, we can construct the broad encoding of the subnormalized Escher transform states, which is the exponential form to the whole matrix we just constructed. So this is the overview of the algorithm. And the complexity here, I just mentioned before. And we can also go further to prepare the more normalized Escher transform state, which is similar to the Gibbs state. Then we just need to apply the additional tech, which is the amplitude amplification, to generate this state. Oh, okay. Because I skipped some technical lemma explanation of this talk, so it goes a bit short. Okay, so in short, our work solved the minimal variety entropy problem with constraint, including make sure the quantum state is valid, and also the expectation of variable under the quantum states. This inspired us to define the quantum Escher transform, but it's more general and is broader, give a broader parameters than the solution to this problem. And also we prove it can be implemented in the algorithm framework based on the broad encoding and QSVT. And we are also thinking about what's the possible applications. Okay, so from the classical Escher transform, there's many applications in finance, including option pricing, importance sampling, and also some application in machine learning, like tilted empirical risk minimization. This is my recent work. And in this workshop, I started to think about quantum Boltzmann machine. So it also give a natural connection to the Boltzmann machine, quantum Boltzmann machine, which is probably our quantum Escher transform is a generalized Gibbs family, and we are trying to think about if we can apply this in some both quantum Boltzmann machine learning models, then use it as the natural update primitive. So that's all. Thank you.
All right. Thanks for a very interesting talk. So I'll start off with some questions. In your early slides, you motivated the problem. If you go back maybe to like even slide 2, I don't know.
Which one?
It was earlier on.
This is classical.
Yeah, even earlier. Yeah. Right here. Okay. So you motivated the problem by we're trying to, make a guess at a distribution that describes what's going on. And you mentioned maximum entropy principle. Then if you continue to maybe the next slide, keep going. Yeah. So it was kind of like all of a sudden this prior distribution P appeared. And I guess the idea is that that is some initial guess at what the distribution is. Is that right?
Here we don't have the assumption on the prior P.
Right, but so the optimization problem is you're minimizing over Q, right?
Yes, yes.
And so I think we can see actually that if P is the uniform distribution, then this is actually just a maximum entropy, like it's a minimum of a negative entropy of Q subject to constraints, which is equivalent to a maximum entropy of Q subject to constraints, right?
So if you make the P as the uniform, then I think it will go back to this, right?
Well, it's maximum entropy with constraints, right? You have these constraints in the first moments.
Yes,
right?
so for this, we can consider the solution is for all P. Then you make the P as the uniform. Then it will go back to the
Okay.
Gibbs state form, to the
Yeah.
Gibbs.
So I guess what you're doing is you're generalizing a bit and you are assuming some priors. That it seems like that, right? Like you even said in your previous slide, prior distribution.
Yes, yes, yes. So
Okay. So like
I
P is
find
some
the
initial
solution.
guess. And then when you go to the quantum case, is it the case that rho is some initial guess on your density matrix?
No. We also consider rho as a general density matrix.
Okay.
Yes.
All right. I have some other questions. So when you talked about the algorithm for preparing the block encoding of the quantum Escher transform. Can you go to that slide?
This?
Yeah, this is pretty good. Is there an assumption on the norm of Hj? Is it assumed to be less than 1?
Yes, it should be bounded by 1.
Okay,
Yeah.
I see. So if that's not there, then we would expect the norm to show up in the number of queries to Uj.
Mm-hmm.
Okay.
Yes.
Because I mean, it seems like what you're essentially doing is this not just a QSVT algorithm to prepare a thermal state in some sense?
Yes, it's very similar.
Okay.
Yeah. We use the
Um,
very similar technique to prepare it.
I see. So you could do like throughout the workshop, we've had there was one 9 hours ago and one 24 hours ago where we we learned about different methods for Gibbs state preparation, and presumably those could also be used for this quantum Escher transform problem. Is that right?
Mm. Mm. Yes, but because we just proposed this new definition, so we at the first beginning we are trying to use the standard to prepare it.
Okay.
Yeah, but if we can like if we find some new ideas on the application, maybe it's also a good idea to use the some new results to prepare the state.
Yeah. Okay. I have a final question. Um, in the quantum Escher transform, there's a theta star that's optimal, right?
Yes.
So do you assume that you know that the what the optimal theta star is, or is like I guess it's implicit in this equation, but it's not clear to me that it's easy to solve for what the lambda star is. Is that right?
Uh, so for this lambda star, we don't have the closed form, and we just have this equation from the constraint, and we think it's hard to solve right now, like using some quantum algorithm. So classically, we can use some gradient descent method to solve it.
Hmm. Okay. So would you modify your algorithm to use the quantum Escher transform algorithm in conjunction with some kind of gradient descent to find this lambda star?
Um,
Or to prepare the optimal quantum Escher transform?
so it might be the follow-up. Yes, we are trying to we make it as the open question in our paper. So
Oh, I see.
probably we try to find a quantum algorithm.
Okay. All right. Um, so there was the talk of Nana Liu that was about 9 hours ago, and that was some work that we did, and that is used to. I think it can be used for this purpose.
Mm-hmm.
So it might be interesting to have a look at that. Okay.
Oh no, the natural gradient something,
It
right?
wasn't that one. It was the quantum thermodynamics and semi-definite optimization.
Uh, is it given by Nala Liu?
That's right.
Oh, okay. Yeah, I would say
Okay.
I will check the paper later.
Sure. Any other questions for Yixian? Okay, we did allocate time for a discussion session. Um, I'm not sure how long the discussion session will go this time, but because one of our speakers had to get running. Does anyone have questions for Yuxuan, our first speaker from this session, or further discussion points? Okay. Does anyone have further questions of Yixian? All right, maybe it's just been a very long workshop over the past 3 days. For myself, I realized the 8 a.m. to 10 a.m. and then the 8 p.m. to 10 p.m. schedule is a bit challenging. So I think everyone is tired. Okay, well, thanks everyone for logging on and participating in the workshop. And thanks to our speakers for this session. The talks were very interesting. And
Organizing this.
oh, sure, very happy to. I really enjoyed it a lot. I learned a lot from the discussions over the past 3 days. It was extremely insightful. So I'm
Yes, I
really
also learn much from the speakers about the quantum Boltzmann machine.
good, good. So I think this concludes our workshop, and thank you for your note, Pratiksha, and thank you for your discussions and questions throughout. So all the talks have been recorded. The plan is to upload them to YouTube, and I know I myself will be going back and trying to revisit many of the discussion points that came up. And the speakers, we've also encouraged them to email slides to Chenkai. And so then the slides will be made available online. And if there's interest, we can think about doing this again next year. We'll just sort of examine the archive and if there's continued activity with quantum Boltzmann machines, which I'm hoping there will be. So okay, good to see everyone, and I think that concludes our workshop. So have a good day, and feel free to stay in touch.
Thank you.
Professor Mark,
Yes.
I have some general questions if anyone doesn't have any specific questions. So
Yeah.
my name is Shiplu. So I'm actually a postdoc researcher in Iowa State. So I
Yeah.
came from a nuclear theory background. Now, as a postdoc, I'm just doing some other stuff too. For example, circuit cutting related to the graph related problems.
Mhm.
So this quantum Boltzmann machine, before I just knew a little bit, but never actually paid attentions, like
Mhm.
what kind of work going on, either classically or using quantum computing. But in one of my work, I have been actually investigating one of the questions. So I'm not trying to invent a new circuit cutting techniques, but um, trying to address those questions using mutual informations, like when you cut into two pieces,
Mhm.
before cutting, if we have a way to identify an optimal cut locations based on the mutual information. So what I've been doing, so let's say I decide like several different cut points and then evaluate like the mutual information between two pieces. And later, when I run the full optimization and try to see whether there is a correlation that exists between, um, you know, um, reconstructed expectation values and mutual information.
Mhm.
But long story short, the way I have been doing, right now I'm just doing some sort of simulation. So, Qiskit, using Qiskit, you can find out like the reduced density matrix using trace, and then you can evaluate the Shannon entropy, and then you can find out the mutual information. But that part evaluation is actually really classical.
Yeah.
So after hearing this talk, I have been actually hearing this talk from the from the very beginning.
Hmm.
What I understand that mutual information is also related to maybe not directly related, like the Boltzmann machine is may not be related to my work, but
Hmm.
somehow, at least for some of the research that they're just trying to evaluate uh, uh, quantum mutual information. And today I just look at one of the papers of your group, and I find out like you have probably a paper on how to evaluate those kind of entropic measures.
Yeah.
So my question is, uh, it's just a suggestions from you. So what is the actually best way of evaluating mutual information between two sub-pieces of a quantum circuit? So let's say you have an arbitrary constructions. Let's say you have an arbitrary circuit. It doesn't matter what does it do. If I'm interested to know the mutual evaluate the mutual information between two sub pieces. So what is the actually best approach to do that on quantum computer?
Yeah. That's an interesting question. So classically, there's a very recognized paper called Mutual Information Neural Estimator, and it's abbreviated as MINE. And what they do is they use a variational formula for relative entropy, which goes by the name Dansker-Varadon. I'll put that in the chat.
Hmm.
Um, so the paper is called Mutual Information Neural Estimator, and they make use of this Dansker-Varadon formula. And that allows you to use so let me step back a bit. Evaluating um, entropy, estimating entropy of a probability distribution is not an easy task. There are some known like sample complexity difficulty results classically, but this approach, this mutual information neural estimator, is kind of a heuristic approach, which people have found, to my understanding, works well in practice. And so um, it makes use of this DV formula. What you do is you take samples from for the classical case, you take samples from a joint distribution, and then you can evaluate sample means of the quantities that appear in this DV formula. And you can try to perform the optimization task in the DV formula using a neural network. So that's what's done classically. Inspired by that kind of thing, we wrote a paper called Quantum Neural Estimation of Entropies. And there is a generalization of Dansker-Varadon to the quantum case that was discovered by Mario Berta, Omar Fawzi, and Marco Tomaschel in the context of quantum information theory. And so we took that variational formula, and the main difference between that and the classical case is that rather than perform an optimization over functions, as you do in Dansker-Varadon, you perform an optimization over Hermitian observables.
Mm.
And so we had to find a way to parameterize Hermitian observables. We did something that I've been learning about this field over the past several years. So what we did was we used a neural network to parameterize the eigenvalues, and we used a parameterized circuit to parameterize the eigenvectors of this Hermitian observable that you optimize over. And the story of the paper was to suggest that and to do some numerical experiments to see how it would perform. And but due to these problems with barren plateaus, it's not clear how well that's barren plateaus with parameterized circuits. It's not clear how well this method will scale. I should also mention that this variational formula that we used is based on something called measured relative entropy. And so you would end up with a quantity that we would call measured mutual information, which is different from the quantum mutual information. At the time, we did not know how to generalize the findings to the standard quantum relative entropy. There is a known variational formula for that, but it's a lot more difficult to work with, and so that was left as an open question. After our work, a paper by Kun Feng and I believe a student working with him, they uploaded a paper called Estimating Quantum Relative Entropy on Quantum Computers, which was an interesting proposal for getting around this problem. And so their technique could be used for this problem. But I believe they're also using parameterized circuits, and so I think they're going to run into some difficulties. And so that's a kind of overview question to your overview answer to your question. But I think there's more work that could be done in this domain to improve these estimators and give better guarantees.
I see.
It sounds like in your problem, though, you might not necessarily need mutual information, and maybe like a correlation measure would suffice, right? And so you might consider like alternate correlation measures besides mutual information, which would be easier to estimate on a quantum computer.
Yeah, I mean, so my motivation of the work was like most of the circuit cutting research to find out an optimal cut locations, they actually design an objective functions based on the floating point operations in classical post-processing phase. But
Mhm.
other than that, most of the researchers they actually did not take into account other factors.
Mhm.
I was thinking like when you partition into two circuits, particularly when they're highly entangled, so we lose some sort of information, and whether that has anything to do with the quality of the reconstructed expectation value or not, in particular in the presence of noise. So, um, yeah, so and then I thought like maybe okay, maybe I don't know how to do it on quantum mechanically. So let's just do some classical simulations and see like what happens to entropy at different cut locations. And when
Mhm.
I do the reconstruction, when I like plot like one along the y-axis, another along the x-axis at different cut locations, so what happens? Uh, so yeah, now that you mentioned, like I could possibly use the other kind of indicator. Maybe fidelity might be and another options.
Really
For,
could be, but that one is also hard to estimate on quantum computers for mixed states.
hmm,
If you're trying to compute the fidelity between a pure state and a mixed state, then that's easy. You can do that. But if you're trying to compute the fidelity of two mixed states, that's known to be a hard problem. The kinds of things that are easy to estimate on quantum computers would be Hilbert-Schmidt distance. So if you were to compute the Hilbert-Schmidt distance between the joint state and the product of the marginals, then that would be easy to do using swap tests, and that might be something to consider for your application.
okay, yeah. Thank you very much.
Yeah. All right. Any other discussion points?
Hi, Mark. I had a question.
Sure.
This is Rahul.
Yeah. Good to
Um,
see you.
yeah. First of all, thanks for organizing the workshop. This has been amazing.
Great.
And also, yeah. So my question is related to one of the open questions raised by Nathan Weeb in his
Hmm.
presentation. So this is related to so he has this open question like how do information bottlenecks form in QBMs?
Hmm.
Um, I was wondering if you had any, like, this is a very vague, like, I don't have any concrete thoughts, but I was wondering if you had any more kind of, I don't know, comments. Like, is the question like related to proving information theoretic lower bounds or like fundamental limitations of quantum Boltzmann machines for certain kinds of learning tasks? Um, I don't know, just I was just wondering what your thoughts were.
Um, it's a good question. I don't have any immediate thoughts on that. Like you know, yeah, I don't have an immediate I didn't think about that question. I've seen the information bottleneck before in the context of quantum information theory. There were some papers about it. But I haven't thought about it deeply in the context of quantum Boltzmann machines. It does sound interesting. Um, I don't have a immediate answer like what that would be useful for, but I am aware of the fact that that way of thinking was very prevalent in classical machine learning and had a strong influence. Um, if you're dealing with QBMs and information bottlenecks, what's nice about a thermal state is we get nice formulas for entropy that we can work with. And if you do things like take the derivatives, as we saw in Nathan's talk, um, nice things can happen. But then when you take a partial trace over some of the systems, it becomes more difficult to work with. And presumably you would be facing some of these obstacles when you think about mutual information and quantum Boltzmann machines because you'll have to you know uh, I think this information bottleneck is relevant for deep learning where we go beyond just visible and hidden, but there are more layers and you're trying to analyze mutual information between the layers, right? And so when we do that, you're going to have to be tracing over some layers of the thermal state, and then that's the object that becomes more difficult to work with. And so, it's the point. It sounds like an interesting research direction, and it sounds like it could lead to something, but there might be some difficulties along the way.
Yeah. Yeah, I was also thinking of, I don't know if you're aware of like some of the work that Robert Wang has done. Like in some of his papers, like for example, he proves, or in those papers, they kind of prove um, that even for quantum machine learning models, like in general, for certain kinds of supervised learning tasks, which involve predicting like expectation values, you would require, like even a quantum machine learner would require at least an exponential number of samples. And they prove this kind of these types of results using like combination of um, like information theoretic lower bounds like Fano's inequality and
Mhm.
Levo's theorem, like those kinds of tools. So I was
Yeah.
just wondering like if those could be somehow used in the context of QBMs to, I don't know, like prove something about the like fundamental limitations on learning using quantum Wilson machines. Um, but yeah, it just, these are just big thoughts. So
Yeah.
um,
No, it sounds reasonable. So, I mean, if Robert Huang was maybe using it in a more general context, and the kind of thing you could look at is evaluating Halevo information with respect to a QBM, and maybe you would get an expression that you could work with to make a statement that's specifically geared towards QBMs. But yeah, I'm not sure beyond that.
Okay, thanks.
Yeah. All right. Any other final discussion points or comments?
Can I ask an IU question?
Sure.
So, as I was like saying before, I'm playing with this Boltzmann machine, like restricted Boltzmann machines, right? And I was also looking at feed forward neural network. So I'm also optimizing the expectation value, but for the Hamiltonian, the chemical Hamiltonian. And what I observed is like I didn't had an idea about how to initialize the parameters, so I was initializing it randomly within a certain range, but that range was selected randomly. But then I came across this Xavier initialization,
What was the
and
term?
I'm not sure how I'm pronouncing it correctly, but it's Xavier.
Xavier. Oh, okay. All right. That's just someone's name, I guess.
Yeah, yeah.
Okay.
They also use the alternate name, which is I think the person's surname, like the final name. But are you aware of that initialization condition?
I'm
Or
not, unfortunately. And is anyone else in the call aware of this?
it's also called GLOROT, GLOROT, GLOROT initialization.
Okay.
Yeah, you might want to check it out. So it came to my surprise. I haven't like read it fully, like how it works, but it's very simple. Like the way you initialize the parameters is for each weight matrix is within the range, and that range is decided by uh, square root of 1 over number of input units plus number of the hidden units for that particular layer.
Okay.
And so the range goes from minus to the plus of this particular number. And surprisingly, it works really well. So it was very much of a surprise for me because I hadn't any idea. But then since I started using that, I'm getting like really pretty good results with the feed forward neural networks that I'm playing around with. So just wanted to ask like whether you had any insights on this or like how it works, or is it like popularly used, or
I've never heard of it before, but that doesn't mean anything because you know, I do consider myself somewhat of a novice, more generally in the theory of machine learning, and my interest in QBMs has picked up just really over the last year, and so that's where I'm coming in at this. Is there theory backing up why this is a good method for initialization? Do you know? Maybe
yeah,
I'm
I think they have a paper on it. I'm kind of putting it here.
okay.
I myself is like I'm also due of like reading that paper, but yeah, there is that one, and then the other one is almost similar, but it goes by other name, like the other author. So I will put that too.
Okay. I've certainly seen this name Yoshua Bengio, which is they're called he's called one of the godfathers of AI.
I see. Yeah, yeah, yeah. And the other goes by HE initialization. Hey initialization. It's I think the last name of the another person. Yeah, just I was just curious about it. Like, yeah, but no worries.
Good. Yeah, that sounds interesting and something that might be useful for quantum Boltzmann machines.
Yeah, yeah,
Okay.
yeah.
Any other comments or discussion points?
I have actually some comments regarding initialization. So recently I have visited couple of papers, uh, which is basically some sort of smart initialization for variational type of algorithms, whether it is used in machine learning or Hamiltonian simulations. That's classical neural network based. So this neural network by itself is not acting as a um, you know, initial quantum state or something, but it's rather helping to find out smart initial values of these parameters. And some of them are based on reinforcement learning, some of them are based on graph neural network, recurrent neural network, and all sort of things people has tried. So I can share some of the resources maybe tomorrow if you are interested in, and you can just look at them.
Yes,
Sure.
please. That would be great.
Yeah, I guess I should comment regarding initialization. There was a paper of Manuel Rudolph, who's a student in Zoe Holmes' group, and this was related to parametrized circuits. And in parametrized circuits, there's difficulties with barren plateaus, as we've discussed. And so, and that has to do with random initialization. And so one thing that they did is they used a classical matrix product state algorithm to find a good initialization. And that was what they called pre-training. And then once that was found, they let's say like lifted the matrix product state construction to a quantum circuit, which they then augmented with further parameters in the quantum circuit. And they found for simulations like on up to 100 qubits that the pre-training would get you to a good starting point, and then the quantum would take over and help you find a lower minimum, than what pre-training would find. And so that was an interesting suggestion that I think has had some impact about using classical and quantum in conjunction. I can try to locate that paper. That was something that we studied when we were doing related things.
Was it a recent paper? I'm trying to look at it. Okay.
Let me find this.
Okay.
I think it had the title Synergistic.
Oh, yeah. Synergistic pre-training of parameterized quantum circuits via tensor networks.
Yeah, let me
I see.
make sure I have the right thing. That's exactly right. Yeah. And
I
this is
see.
an archive. The archive version is a different title.
This
That
one.
is this one. Yeah, they're the same. That's exactly right. Yeah.
Mm-hmm.
So that was an interesting paper.
Yeah, I will look at it. Oh, this is nice.
I don't think anyone has used that in the context of QBMs. That could be interesting. But with QBMs, there's less known about the barren plateau problem. Like as we discussed in the first day, the main result there is from Nathan when there's too many visible units and too much entanglement. Okay. Well, if there are no other discussion points, I will thank everyone once again and wish you well.
Thank you. Bye-bye.
All right. Have a good day. Bye. Thank you.